Hi, welcome to this video on Rust lifetimes. My name is Doug Milford from Lambda Valley. Lifetimes is a difficult topic for most to learn, including seasoned developers. It's a topic that's a pretty specific one to Rust due to the memory management trade-offs Rust has made. Before you begin this video, you should understand Rust memory management through ownership and borrowing. If not, please review my video on that before trying to tackle this topic. In the case of Rust lifetimes, it was a new concept to me and I struggled to learn it at first. If you struggle with lifetimes yourself, you've got some pretty good company, so don't beat yourself up. So what are lifetimes? Rust allows one and only one owner of memory, but you're allowed to have multiple references to that memory. Lifetimes are a way of enforcing a piece of memory is still valid for reference. I want to hammer home that lifetimes are about references and how to handle a bear trap that happens around them. I'll touch upon this multiple times in the video to help drill in the concept. Confused yet? Stick with me and power through. We're going to go through several examples to demonstrate. Let's start with a very basic example of a very specific problem with references. Let's create a variable a, but delay assigning it until later in the code. I'll now create an artificial inner scope by placing some brackets. Inside of that, I'll create another variable called b, and I'll just make it a string of howdy. It could have been a struct, enum, vector, whatever. The data type isn't relevant. Before I go any further, I want to remind you that b's memory is cleaned up once it hits the end bracket. I could have passed the ownership of memory to a if I'd like, and now Rust knows not to clean that memory up until a goes out of scope. The variable b would no longer be associated with any memory. When the end bracket is hit, now no memory gets cleaned up because it's already been transferred to a. And now I can print a after the artificial inner scope, and it works fine. So far you should be thinking, well, so what? This code compiles because ownership was transferred from b to a. But what if all I wanted to do was reference the memory in B, not take ownership? As a reminder, Rust allows one and only one owner of memory, but allows multiple references as long as you won't be mutating that data. We now get a compile error saying B does not live long enough. Because ownership of the memory never gets transferred to A, the memory that B owns is cleaned up at the end of the inner scope. A is now referencing garbage. And Rust won't allow that. So lifetimes are really about ensuring memory does not get cleaned up before a reference can use it. I'll repeat that because it's too easy for it to just wash over you. Lifetimes are really about ensuring memory does not get cleaned up before a reference can use it. As we've already seen, transferring ownership is not a problem. It's all about the references, baby! This is a bit of a contrived example. Although it's often used to illustrate the issue at hand, it doesn't address how lifetimes come into the picture yet. Let's clean up and do some examples. I'll create a simple function that takes no parameters but returns an integer reference. You get a compile error stating that this function's return type contains a borrowed value, but there is no value for it to borrow from. Consider giving it a static lifetime. So if you're not going to return a static variable or a constant, which for the sake of argument we're not for the moment, Rust will have issues. What's going on here is that the compiler knows that since no references were passed into the function, that means the borrowed reference would have to originate from inside the function. Rust also knows that any variables created inside the function will have their memory cleaned up once it goes out of scope. So before I even call this function, Rust knows that there's no way you're ever going to get away with this half-baked scheme. It's similar to the situation where we had our inner scope. Memory gets cleaned up before the downstream code has a chance to use it. The life of the memory we're returning is not long enough. If, instead, I return back the ownership of the memory instead of the reference, it works as expected. There's no possible way code downstream is reading garbage data. We just get a warning that our function has never been used, which we can ignore for the moment. Let's get back to our error. Just so you know, I'm using an i32 for demonstration purposes. I could have used any data type, such as a string, vector, struct, enum, whatever. It doesn't matter. The issue comes back to how long a reference can be expected to live, regardless of the memory type or if the memory is on the stack or the heap. Stay focused on the fact that the issue is due to references. Back to our example. I'm going to modify this to pass in a reference and we'll just return the same exact reference. We get a warning message that the function is never used. We'll use it in just a second to get rid of that warning. So why does this function compile when the other one didn't? We're still passing back a reference to an integer. Well, Rust can guarantee that the returned reference will live long enough for downstream code to properly use it. The scope that is providing the reference is the same exact scope that will be receiving the result output. Let's create an integer within the main. We'll call our function passing in a reference to our variable. The result data is just a reference to our original data. And let's print it to the terminal so that we're doing something with it. Rust can logically see that the scope of the input parameter is within the same scope of the output. If it's in the same scope, it can guarantee the memory is still valid at this point. In other words, both are accessing memory that lives to the end of the scope bracket, hence the name lifetime. The way Rust denotes a lifetime is with a generic symbol in angle brackets that has an apostrophe in front of it. It's convention to use the lowercase a for the first lifetime, b for the second, etc., but you use whatever you like. It can even be multiple characters to be more descriptive. The important piece is that it has the apostrophe in front. For this example, I'll just use a standard notation, which is fine. Once you tell a function you're defining a lifetime, you can apply it to whatever input or output variables that apply. Let's apply it to both our input and output. This is saying I'll define some generic lifetime and make sure that my input and output comply with it, meaning the input memory exists in the same scope as the output memory and thus live the same length of time. There's a caveat to that, but we'll get back to that in a minute. This notation used to be how every function was defined back in the old days. All references used to need an explicit lifetime. It's certainly more verbose than what you might be used to. It may take some time for your eyes to adjust to the syntax. Even though you may have written your own functions without explicitly defining lifetimes for your references, they were there in the background. You just didn't know it. The Rust team realized that in many cases, they could determine the lifetimes without making the developer define it explicitly. So they automated it for those situations and created a compile error in situations where it couldn't quite figure it out on its own. When you write a function, the compiler will look to see what parameters are references. If it sees one, it creates a lifetime for it and assigns it to its parameter. If it sees another reference in your parameters, it will add another lifetime and assign it to that parameter, and so on and so forth. It will add as many lifetime definitions as it needs to cover the references in the parameters. If you have any parameters that are not a reference, it does nothing with those, as those don't cause the issue related to referencing old, cleaned up memory. If you have an output that is not a reference, then all that work the compiler did to implicitly include lifetimes really wasn't helpful, because that will never have the issue we've described, so no harm, no foul. If you do have it as a reference, then the compiler has to know what lifetime to assign the output. That's where some of the trickiness comes into play, and I'll be touching upon that further in the video. What about static or constant variables? Can those be used as reference parameters? Well, static variables and constants are valid for the life of the program, which means their lifetime is the entirety of the application, so I don't see why not. Rust has a special lifetime notation for that of apostrophe static. I'll create a constant at the top of the file here. Rust will automatically assign the static lifetime to constants. And now I'll use that as my input just fine. Rust will know to treat your result with the same exact lifetime as the constant itself. Okay, let's get rid of that and remove some clutter. What happens when I add another parameter? For the moment, I'm going to pass it in straight and not as a reference. I'm going to create another variable and pass it into our function. Will this cause a problem? Well, it compiles, but we get a warning because our parameter is never used. Let's print it to the terminal just so that we're doing something with it. So we didn't define a lifetime on param2, nor should we. It's not a reference. If I even try to put a lifetime on it, it won't compile. What do you think would happen if the second parameter was a reference instead of a non-reference? Let's remove the lifetime for param2, but we'll make it a reference. I'll also need to fix the calling code to pass in a reference instead of the variable itself. So this compiles because it can see that param2 is not the one being returned, and thus it never has a conflict with the output's lifetime. Therefore, we currently don't need to explicitly state the lifetime for param2, but it does have a lifetime defined in the background, even though as the developer we haven't explicitly defined it. Let's create a second lifetime called b and apply it to our second parameter. This is how the compiler understands it if we didn't explicitly define the lifetime on param2. For every input reference that doesn't have an explicitly defined lifetime, it will be given its own lifetime. Param2 never has a chance to be returned as the output, so Rust knows it's okay for param2 to have a different lifetime. Let's twist the knife a little. If it's possible for param2 to be returned, that complicates the story. Let's create an if statement and return back the greater of our two parameters. We get a compile error. If I hover my mouse, it says there's a lifetime mismatch. And it's true. The output has one lifetime denoted by A, but at some point we're returning a lifetime denoted by B. Rust can no longer guarantee that code downstream will be okay. The second lifetime parameter could be bigger or smaller. There's no way for Rust to know. The output variable could potentially outlive the reference lifetime, which is a problem. One possible solution is to tell the compiler that B has to live at least as long as A. The way to do that is to put a colon and the A. This is called lifetime subtyping, and it works just fine. But it's a little verbose, and it's probably overkill for most of your needs. As a developer, we can look at the calling code and say, yeah, our two input parameters are within the same scope. The result should be fine either way as the inputs have the same lifetime. But Rust wants a guarantee that's always the case, not just the code you're currently looking at. To do that, we simply make sure param1 and param2 are of the same lifetime. And we'll get rid of the B altogether as it's no longer needed. Now the lifetimes are guaranteed to meet my needs. This may seem like it forces everything to have the same lifetime for the calling code parameters. Not really. If you have the same lifetime definition across several parameters, think of it as the minimum of the passed-in lifetimes for any given call, which gives it a bit more flexibility. Let's do a realistic example that many people run into. Often developers need to compare one or more string slices. So they happily create a function that accepts two string slices, and as a simple example, let's say we return the best one. Then the developer hits this compile error about lifetimes and they foam at the mouth with frustration. I'm just trying to do something simple. Why is it giving me this issue? I'm talking from personal experience here. The developer doesn't realize the potential danger of the dangling reference that we've been discussing. And why should they? Their calling code doesn't have different scopes, so they shouldn't have to worry about lifetimes. Rust wants to ensure the function definition itself is okay, not just your current calling code. Often the solution is just to tack on an explicit lifetime and be done with it. You might be wondering why Rust doesn't automatically assign the same lifetime to all parameters. Wouldn't that be easier? Well, for the examples I've done, yes, and often that's how you fix lifetime issues. But functions will frequently take multiple reference parameters, most of which don't get returned as an output. You would have to write much more lifetime definitions if Rust defaulted to the same lifetime for each of those. The reason lifetimes is considered a specialized topic in the first place is because Rust did a good job of automating a vast majority of it for you, and they could still come up with ways to automate even more in the future. They've only automated the low-hanging fruit at this point. You as the developer are just filling in the gaps that Rust couldn't figure out on its own from its default settings. Perhaps in the future, lifetimes will become fully automated. Who knows? Let's clean up and do some example functions to help cement some concepts. I'll create a function with a single parameter. I'm going to switch to vectors now just to switch it up. What lifetimes would Rust infer from this? Trick question. Lifetimes don't apply because there are no reference inputs or outputs. What about this one? We have a single parameter reference, but a non-reference for the return type. Although you have a reference input, lifetimes aren't an issue because there's no reference output. That doesn't mean the lifetime doesn't exist on the parameter. The compiler still sees it like so. It just has no effect on the output, so it doesn't care what the input lifetime is, and thus doesn't force you to explicitly define it. What if we had a reference output, but no reference inputs? In this case, it's missing a lifetime specifier, so let's give it that and see what it does. This is similar to earlier in the video when we had no parameter. Since ownership of the memory gets transferred to this function, that memory will now get cleaned up once it hits the end bracket. We can't pass back a reference, or else the receiving variable will be referencing garbage memory. Lifetimes don't apply because there are no reference inputs. The caveat is that if we want to return a static lifetime reference, we could do that. Let's clean up and do some more complex examples. I'm going to create a test function with multiple parameters, some of which are references, some of which are not. I'll create an if statement, and I'll try to incorporate our non-reference parameters in here so that at least we're using them. And if it's true, we'll pass back param2. If it's false, we'll pass back param3. Okay, so we get some compile errors. If I hover my mouse, you can see that it's related to lifetimes. Let's fill in the implied lifetimes the way the compiler would see it, and then we'll fix it. The compiler sees two parameters as references, params2 and 3. So it creates two lifetime placeholders. It applies lifetime A to param2 and lifetime B to param3. If we had a third parameter as a reference, it would create a lifetime C and apply it to that, and so on and so forth. For the output, it doesn't know what the heck it wants to do with that, so we'll leave it for now. This is what the compiler believes your intention to be. A vast majority of the cases you can say, whoa, I don't need to support different lifetimes for different parameters, so I'm going to explicitly define a single lifetime and apply it to everything. This is what you, as the developer, would have written to force the lifetimes to be the same. Rust just had some edge cases that you may not have intended and realized there'd be a problem, hence the compile error. Therefore, you just need to step in and say, I only wanted to support the same lifetime, or whatever lifetimes fits your needs. If I included reference parameters that didn't have a chance of being returned, then I'd be okay in not putting an A lifetime on them. It's okay that they would have their own lifetime, and the default that Rust provided would be just fine. In this example, all reference parameters have a chance of being returned, and that's why I've explicitly forced them to be of lifetime A. Rust will ensure that whatever your scheme, memory issues won't occur. There's a special case that Rust will handle automatically, and that's if you have a single input reference and an output reference. You could have more non-reference inputs, and this would still apply. It doesn't really matter what you would do in the body, so I'll just return param A. Rust still applies the lifetimes to the parameters like it did before, but if there's only one input reference, it will force the output reference to have the same lifetime. There's no confusion in the situation, so you will never have to explicitly define lifetimes here. Rust can safely assume this is what your intention was. Let's clean up to explore vectors. I'll create a function that takes in a vector slice reference or array reference, and let's return back the same type. I'm actually going to return a slice of the parameter, not the entire parameter. We'll call our function in the main by creating a vector. And let's pass that into our function. And then finally print out the results. So here we're not passing back the entire reference, just a slice of it. This is perfectly legitimate. If an entire vector has a certain lifetime, then all of its elements have that same lifetime. Even though you're only returning a subset or a slice, Rust will compile just fine. let's augment our function to take a second parameter of the same type. We'll put a little logic in the function body to be based on an if statement. And let's just return a slice of a vector in each branch. Now, just like we saw in previous examples, the compiler can't implicitly determine what the lifetime should be. It's currently assuming param1 has one lifetime and param2 has another, and God knows what the output lifetime is. So as the developer, we say to ourselves, do I really need param1 and param2 to be of different lifetimes? No? Okay then, let's tell the compiler it's not really necessary to support that and put the same lifetime on each. And now all I have to do is call the function with valid data and we're off to the races. And now our compile errors disappear. So we did this for the vector. As a reminder, strings are just vectors of U8s. So the same concept applies. String parsing is often where people run into issues with lifetimes, but now you know better about what's really going on. Okay, let's clean up and address the static lifetimes I keep talking about. Static just means that it's a lifetime that lasts the entire program. Constants are static by their nature. You can also have static variables, which is beyond the scope of this video, but they would behave the same. Let's just create a couple of constants at the top of this file to play with. We'll write a function with no parameters that returns a static variable. Just use the apostrophe static where the lifetime notation would go on your reference. Rust has reserved the lifetime notation of apostrophe static. You don't need to define it in angular brackets like you would for apostrophe A. It's just part of the language. And from there, I can do my logic and return back a constant which has a static lifetime. So that's the exception that a reference output needs to return a reference parameter. But it's not limited to outputs. We can have static inputs as well. Let's create two parameters, both with a static lifetime. And let's just do a little logic to return the greater of the two. And we'll just call it. And print out the results. When you're defining the parameter lifetime as static, you're really constraining what can be input into this function. When I create another variable and try to pass it into our function, we get an error that A does not live long enough. The function requires that it lives the entire length of the program, which is a pretty high bar to get over. Instead, I can use an explicit lifetime instead of the static, and that will work for all situations. It has no problems accepting or returning static variables. And now everything compiles fine. Okay, let's clean up again. How do we use the lifetimes with generics? I'll create a function that gets the smaller of the generic t, meaning I'll need it to be constrained by the type of partial ORed. In the body, I'll just return the smaller parameter. We get our favorite compile errors, but we've solved this problem multiple times before. Just because we're using generics doesn't make it any different. We actually define lifetimes in the same angle brackets as the generics, so it might feel a little wonky at first. The compiler knows that because you have an apostrophe, you meant for it to be a lifetime. And now we just apply it to our parameters and outputs. Bingo! No problem! Now I can use this function for multiple types. Let's create a couple of floats. And let's use the function to find the smaller. We can do the same thing for string slices. And let's use the generic function to find the smaller of the two. Any data type that implements the trait partial ORed will work. Even your own custom struct. It doesn't matter. And as a reminder, it doesn't matter whether the memory is on the stack or the heap. It works the same. Let's clean up for the next section. Structs can also have lifetimes. Let's create a simple struct and let's give it some data. Now, just like with functions, struct lifetimes are only concerned with references. Currently, I have some data that's not a reference, so there's no lifetime issues. But let's add another field with some reference data. We get our familiar compile error. Since Doug struct has its own memory, but references some memory outside of itself, you need to make sure the reference lives long enough where it doesn't leave Doug struct referencing bad memory. So let's give it a lifetime. And now let's apply it to the reference. And now we're ready to rock and roll. This seems trivial, and you may be wondering why we need to go through the ceremony. If we had another reference, we'll be able to define a second lifetime. And this says, hey, I'm going to have two references, but they don't have to be the same lifetime. We can even go further and say that lifetime B has to be at least as long as lifetime A, with a subtype similar to what we did with a function. I haven't found much need for this syntax because usually if I have two references, they're within the same scope and automatically have the same lifetime. However, if you see this syntax, at least you'll know what it's saying. Well kids, that pretty much wraps it up for this video. If you're still foggy-headed, that's to be expected. This isn't a topic most people pick up on first pass. I recommend you play around a bit and get your hands dirty. Thank you very much for watching. Once again, my name is Doug Milford from Lambda Valley, and I'll see you next time.